Hello, everybody. Welcome back to another lecture in Geography 340 Climatology. I'm Dr. Zach Hilgendorf. Today, we're going to be talking about cloud formation again, our second lecture on this kind of broader topic of cloud formation, frontal movement, air parcels, and precipitation. This lecture is going to be a bit shorter, but it's going to focus on adiabatic processes. It's going to start us looking at how vertical displacement of air parcels impacts the condensation deposition rates or warming rates of air parcels moving throughout our atmosphere. And this generally corresponds to how different types of clouds form. So we talked about in the last lecture, how is air cooled to its dew point? There were two different possibilities. We had diabatic cooling and adiabatic cooling. So diabatic processes were any temperature change not related to the vertical displacement of air, adiabatic vertical displacement of air. So things like changes in the warmth and moisture within water or land and how those interacting air parcels would cool as a result or warm as a result and mix. Adiabatic processes deal with the changing temperature of a parcel of air due to the air rising or sinking adiabatically. It assumes no heat, mass, or momentum pass across that air parcel boundary. And these rates are not static. They change and occur differently depending on whether or not that air or that parcel of air is saturated or unsaturated. So let's look at adiabatic processes in the atmosphere, or at least a simplified version of that. So let's pretend we have these air parcels here. So as we start, air pressure decreases with altitude. We know that. And as it does, that parcel of air expands. Likewise, as it decreases, it warms and condenses. So we have something to start off with called the dry adiabatic lapse rate. And what that says, it's the adiabatic rate of cooling or warming of an unsaturated parcel of air. Now, that rate of change is pretty consistent at about 1 degree Celsius per every 100 meters, 10 degrees Celsius per every kilometer. That number should sound familiar because all of you have taken Geography 104, and this was something we talked about in the Moisture in the Atmosphere lab, the Mount Doom lab, where you're tracking a parcel of air moving up and over a mountain chain in Northern California from Eureka to Redding. So let's take a look at kind of what that looks like and how you would calculate kind of how that parcel of air and the temperature within that air parcel changes. So in our start, at ground level, we have a parcel of air where the air temperature is 35 degrees Celsius in that parcel. The dew point is 25 degrees Celsius. So if you're rising at and cooling at the dry adiabatic lapse rate, 1 degree Celsius per every 100 meters, by the time you get up to 500 meters into our atmosphere, you would cool 5 degrees. So the parcel of air, the temperature of that parcel of air would be 30 degrees Celsius. But would our dew point be 25 degrees Celsius? Pause on that for a second, because the dew point doesn't change here. Now, in 104, we assumed that the dew point does not change as long as the parcel of air is dry. We'll find out that's not necessarily the case. So as you get up to 1,000 meters, again, our dew point is 25 degrees Celsius. Here, our parcel of air remains cooling at another 5 degrees Celsius. So now we've gone up a kilometer. We are down 10 degrees Celsius to 25 degrees Celsius. Once we get to that point where our dew point and our air surface or our air parcel temperature are equal, that is what we call our lifting condensation level. So the lifting condensation level is the height at which the rising air that is cooling at our dry adiabatic lapse rate becomes saturated. It meets that dew point temperature and condensation can begin, or will begin. That's where we have our clouds. The lifting condensation level is the base of our cloud height. We look here, see that flat base there on all of these beautiful little clouds wandering across the sky, that base is our lifting condensation level. One problem with that, as I alluded to, dew point does not stay the same within a parcel of rising air. We assumed it did in 104 for the sake of simplicity, but for the sake of reality, that's not the case. What happens to air pressure in a parcel of air as it rises? Well, it expands, right? Well, what then happens to the partial pressure of each gas in a parcel as it rises? So let's look here. We've seen this in a number of different lectures before. Here's our saturation vapor pressure on the vertical axis, temperature on the horizontal. Our initial dew point is 25 degrees Celsius in our example, right? So that initial vapor pressure is going to be about 31.7 millibars. At 500 meters, air pressure is about 5.5 degrees less than it is at surface. So at 500 meters, our vapor pressure is about 30 millibars, which means our dew point has changed. At 500 meters, our dew point is actually about 24 degrees Celsius. So let's go back here to the same figure we were looking at before. We've moved up to 500 meters in our atmosphere. Our air parcel has cooled down to 30 degrees Celsius. Our dew point has actually changed and cooled because that vapor pressure is changing to about 24 degrees Celsius. At 1,000 meters, our air parcel is about 25 degrees Celsius. It's cooling at another 5 degrees as it's risen another 500 meters. Our dew point is going to move down to 23 degrees Celsius. So that change is what we call our dew point lapse rate. And it's just like the dry adiabatic lapse rate or the saturated lapse rate, which we'll talk about here in just a little bit. It's just a different lapse rate to look at how the temperature or dew point within a parcel of air is going to be changing based off of the atmospheric differences that that parcel is subject to as it rises through the air. Now, the dew point lapse rate, or the DPLR, is roughly about 0.2 of a degree Celsius for every 100 meters. So as you see, as we go from surface to 500 meters, we go down a single degree Celsius, so 2 degrees Celsius for every 100 meters. Same thing as you get further up into the atmosphere, it drops down after 1,000 meters or a kilometer, it drops down of 2 degrees Celsius. So once it gets up here to the new lifting condensation level, because it's not the one that we looked at previously, because our dew point lapse rate needs to be taken into account, our dew point and air parcel temperature will meet 22.5 degrees Celsius, an altitude here in this example of 1,250 meters. So we know our dry adiabatic lapse rate is 1 degree Celsius for every 100 meters. We know our dew point lapse rate is 0.2 of a degree Celsius for every 100 meters. What happens once you get to saturation, once you hit that lifting condensation level? So here, the height of our lifting condensation level can be determined by using this equation. So air temperature at surface minus the dew point at surface divided by 0.8 degrees Celsius divided by 100 meters. Or you can use it this way. Height of the LCL is equal to, in kind of broader brackets here, air temperature at surface minus dew point at surface divided by 0.8 of a degree Celsius times 100 meters. So once we hit that point, we have to change our lapse rate that we're using. We have to shift to using our saturated adiabatic lapse rate. So saturated adiabatic lapse rate is just that rate of cooling or warming that occurs in saturated air. The rate of temperature change is typically between about 4.4 to 0.9 of a degree Celsius per every 100 meters. So we're at 1,250, we're rising to 1,500. Our clouds are continuing to form here. In this example, we're going to assume that we are changing by a ½ degree Celsius for every 100 meters. That's not the case. Like I said, it fluctuates between 0.4 and 0.9 degrees Celsius, typically. So if we take that into account, we're at 22.5 degrees Celsius for our parcel of air. We rise another 250 meters into the air. We'll drop to 21.25 degrees Celsius for our parcel of air temperature. The dew point will change at that same rate now. The dew point is changing at the saturated adiabatic lapse rate after you've reached the lifting condensation level. Prior to, they change at different rates. The air parcel will change at the dry adiabatic lapse rate. The dew point will change at the dew point lapse rate. But once you hit that lifting condensation level, both are fluctuating at the saturated adiabatic lapse rate. That's something really important to note. So what happens then when you have descending air? Because we know as air rises, it cools, as air descends, it warms. So immediately you're going to have a change in how we have to calculate rates as air descends. So here is our same parcel of air at 21.25 degrees Celsius for the dew point and air parcel temperature. And we're going to be decreasing all the way back down to the surface. We see that air is condensing. So one thing we need to do and note is that descending air warms. So we will assume that air temperature and dew point are immediately different. So we need to go back to using our dry adiabatic lapse rate and our dew point lapse rate to add to our temperatures as they decrease. So we were reducing temperature as we rose. We're adding temperatures and increasing our temperature as we decrease. So what's that going to be? Go ahead and take a second to pause. Use those dry adiabatic lapse rates of 1 degree Celsius for every 100 meters and a dew point lapse rate of 0.2 degrees Celsius for every 100 meters. So go ahead and pause and see if you can figure this one out. All right, so we dropped 1,500 meters from 1,500 to 0. So you're adding 15 degrees Celsius to your temperature. So our air parcel temperature will rise to 36.25 degrees Celsius. And our dew point will also rise somewhat, about 3 degrees Celsius for that 1,500 meter drop to about 24.25 degrees Celsius. So there we've kind of done our first little foray into adiabatic processes. And there is a type of fog that adheres to this process. So here we see upslope fog along the front range of the Rocky Mountains. Upslope fog, or Cheyenne fog as is also named, occurs when sloping terrain lifts air, cooling it adiabatically to its dew point and saturation. Upslope fog can be viewed as either a stratus cloud or a fog, depending on the point of reference or the observer. Upslope fog generally forms at higher elevations and builds downward into valleys. So there, like I said, we've kind of completed talking initially about adiabatic and diabatic processes. In the next video, the following week, we're going to be looking at how air parcels and frontal systems operate. From there, it's going to build on some of the adiabatic and diabatic processes we've been talking about. From there, we're going to be diving into the major cloud types and how they form. And then following that, we're going to be moving into precipitation. So all the different types of precipitation, from rain to sleet to hail and many more. So I will see you all in the next video, and I hope you have a great day. Thank you.